We'll start in 1 minute. Today we'll continue the final exam review. Remember that the final exam is over everything. And the date and time for the final, May 3rd, on Monday from 10 a.m. to 12 p.m. We'll finish up the part 1 from last time. So we were looking at improper integrals and the comparison test. So this right here, find the sum of the power series. Well, that's not supposed to be there. We're just going to determine if this improper integral converges or diverges. The integrand is 1 over the 4th root of x to the 4th minus 0.08. So the 4th root of x to the 4th is x. So this looks like we should be able to compare it with the improper integral of 1 over x. Okay, so we'll do a little bit of preliminary work for x greater than or equal to 1. The 4th root of x to the 4th minus 0.08 is less than the 4th root of x to the 4th. But the 4th root of x to the 4th is x. And so if the 4th root of x to the 4th minus 0.08 is less than x, then the reciprocal 1 over the 4th root of x to the 4th minus 0.08 is greater than the reciprocal of x, which is to say that it's greater than 1 over x. So this should mean that the improper integral of 1 over the 4th root of x to the 4th minus 0.08 dx, that should be greater than the improper integral of 1 over x from 1 to infinity. So if we can show that the improper integral of 1 over x from 1 to infinity diverges, then this other improper integral must also diverge, since it has to be greater than infinity, so to speak. Well, we already know the answer, but if you're going to show work on a final exam problem, you'll do it this way. Write down the improper integral from 1 to infinity of 1 over x dx. And then this is the limit as b approaches infinity of the definite integral from 1 to b of 1 over x dx. And this is the limit as b approaches infinity of the natural log of x from evaluated from 1 to b. Okay, so the limit as b approaches infinity of the natural log of b minus the natural log of 1. The natural log of 1 is 0, but as b approaches infinity, the natural log of b is also infinite. So this limit diverges to infinity. So for convenience, we just say that it's infinite. And so by comparison, this shows that the original improper integral diverges by comparison. Okay, so that's all there is to that. Got it. All right, let's move on to the next page. Chapter 8 material to review. So the arc length formula, if the first derivative of f is continuous on the closed interval from a to b, the length of the curve y equals f of x on the same interval from a to b is the definite integral of the square root of 1 plus the square of f prime of x dx from x equals a to x equals b. In Leibniz notation, you could write it in this form. Instead of f prime of x squared, you could write dy dx squared. All right, so we'll find the length of the curve of the function f of x equals e to the x over 4 plus e to the negative x on the interval from x equals 0 to x equals 1. So we need to find the derivative. So the derivative of e to the x over 4 plus e to the negative x is e to the x over 4 minus e to the negative x. We can think of this as e to the x over 4 minus 1 over e to the x, and then with a common denominator, 4 times e to the x, we can write this as e to the 2x minus 4 over 4 times e to the x. To use the arc length formula, we have to square the first derivative. So if we square f prime of x, the denominator, when we square that, that will become 16 e to the 2x. And then in the numerator, we square e to the 2x minus 4. So we'll get e to the 4x. And then minus 4e to the 2x twice for a total of minus 8e to the 2x. And then finally, negative 4 times negative 4 is positive 16. Then we have to add 1 to this. have f prime of x squared plus 1. Notice that when we add 1 to this, and then with the common denominator of 16e to the 2x, we're going to be adding 16e to the 2x over 16e to the 2x. So after doing that, this numerator will be e to the 4th plus 8e to the 2x plus 16 over 16e to the 2x. Because adding 16e to the 2x to negative 8e to the 2x results in positive 8e to the 2x. This is the expression that goes inside the square root. But notice that it's a perfect square in the numerator. If we square the term e to the 2nd plus 4, we get this numerator, e to the 4th plus 8e to the e to the 2x is what I want. I want e to the 4x there plus 8e to the 2x plus 16. Okay, I think we're okay now. And then the denominator is also a perfect square, 4e to the x squared. Okay, so in the integral, we'll have the interval is from 0 to 1. And then the square root of this perfect square, we're just going to get e to the 2x plus 4 over 4e to the x dx. We'll take this a couple of steps further. Since there's just one term in the denominator, we can write the separate terms. So e to the 2x divided by 4e to the x. That becomes e to the x over 4. And then plus 4 over 4e to the x is just 1 over e to the x. But for convenience, I'll write it as e to the negative x because we want to find the antiderivative. And then evaluating this integral is pretty simple. An antiderivative of e to the x over 4 is just e to the x over 4. And an antiderivative of e to the negative x is negative e to the negative x. And then we evaluate this from 0 to 1. So when x is 1, we get e to the 1st over 4 minus e to the negative 1. I'm going to write it as minus 1 over e. And then from that, we subtract when we evaluate this with x equals 0. So e to the 0 is 1, so it's minus 1/4. And then minus e to the 0 again is minus 1. Okay, we can simplify a little bit more, but I'll leave the rest of that for you to do. That is the length of the curve. Okay, another formula from chapter 8, the area of a surface of revolution. On an interval from a to b, the x values are from a to b. And if we let y equals f of x be greater than or equal to 0, let that be continuous and differentiable, then the surface area generated by rotating y equals f of x about the x-axis is given by this formula. It's the definite integral of 2 pi times f of x times the square root of 1 plus the square of f prime of x dx from a to b. And the Leibniz notation for the derivative, instead of f prime of x, you can write dy dx. And you can also replace f of x with y. In this example, find the surface area generated by rotating f of x equals x to the third plus 1 over 12x on the interval from 1/2 to 1 for x, and we're rotating about the x-axis. So before we use the formula, we have to find the derivative of f. So f prime of x is 3x squared. And then the derivative of 1 over 12x is minus 1 over 12x squared. If we write this with a common denominator of 12x to the second, we'll get 36x to the fourth minus 1 all over 12x to the second. And then we're going to square this derivative. So when we square 36x to the fourth minus 1, 36x to the fourth quantity squared is 1296x to the eighth. And then we're going to have minus 36x to the fourth twice for a total of minus 72x to the fourth, and then plus 1. And then when we square the denominator, we get 144x to the fourth. Just like we did in the previous example, we have to add 1 to the square of f prime of x. So f prime of x squared plus 1. So notice when we add 1, we're really going to be adding 144x to the fourth over 144x to the fourth. And then when we add 144x to the fourth to minus 72x to the fourth, we'll end up with plus 72x to the fourth in the numerator. So we'll just write that 1296x to the eighth plus 72x to the fourth plus 1 all over 144x to the fourth. And this is a perfect square in the numerator and a perfect square in the denominator. This is what's going to go inside the square root. So in factored form, the numerator is 36x to the fourth plus 1 quantity squared. And the denominator is 12x to the second squared. Okay, now we can use the formula for the surface area. The interval is from x equals 1/2 to 1. And then 2 pi times f of x. F of x is x to the third plus 1 over 12x. And then we're multiplying this by the square root of this quantity, which is the f prime of x squared plus 1. So when we take the square root, we'll just get 36x to the fourth plus 1 over 12x to the second dx. I'll take it a couple of steps further. It's pretty simple from here, but So what I'll do is rewrite this term, 36x to the fourth plus 1 over 12x to the second, as the sum of two terms. And so we'll get 3x to the second plus 1 over 12x to the second. Okay, one more step. So let's just multiply those two quantities. X to the third times 3x to the second is 3x to the fifth. And then plus x to the third times 1 over 12x to the second is x over 12. And then 1 over 12x times 3x to the second is x over 4x. Sorry, x over 4. Yeah, x over 4. And then the last one, 1 over 12x times 1 over 12x to the second is 1 over 144 x to the third dx. Okay, I'll leave the rest of that for you to do. Let's move on to the next page. So we review hydrostatic force with an example. An 8 feet by 6 feet rectangular vertical plate is submerged in water with one long side at the water surface. Find the hydrostatic force against one side of the plate. Okay, so if we have the surface of the water and then 8 by 6 feet. So it's a vertical plate submerged in water. So the depth will range from x equals 0 to x equals 6. So our interval for x values are from 0 to 6. And if we pick an arbitrary interval, of length delta x at depth x sub I feet, then we can write down an equation for the hydrostatic force on that little rectangle. So hydrostatic force F is rho times G times the area times the depth. If A times D is measured in cubic feet, A times D is the volume in cubic feet, then rho times G is the number 62.5 pounds per 1 cubic foot or per cubic foot. Okay, the area is the area of this rectangle. The long side of the rectangle is 8 feet. The short side is delta x. And the depth, if we take a arbitrary point on that subinterval and call it x sub I, then x sub I is the depth. So for that particular rectangle, the hydrostatic force, we'll call it f sub I is 62.5 times 8 times delta x times x sub I. And if you would rather write it as, let's see, we can multiply 8 times 625. That's just 500. Write it as 500 times x sub I times delta x. Okay, so you'll remember the idea is we can do that for all of the sub-rectangles, for any number of sub-rectangles. And if we add up the hydrostatic forces on all of those, then we can take a limit which will be equal to the definite integral from x equals 0 feet to x equals 6 feet. And the integrand is 500x times dx. Okay, so evaluating that is pretty simple. I'll leave the rest of that for you to do. But this hydrostatic force will be measured in pounds. Okay, another topic from chapter 8 have to do with moments and center of mass. So in this setting, let R be the region in the xy plane with uniform density rho between the graph y equals f of x, the x-axis, and the vertical lines x equals a and x equals b. The moment of the region about the y-axis is denoted capital M sub y, and that's equal to rho times the definite integral of x times f of x dx from x equals a to x equals b. The moment of the region R about the x-axis is denoted capital M sub x, and that's equal to rho times the definite integral of 1/2 the square of f of x dx from x equals a to b. And then the mass of that region is rho times the definite integral of f of x dx from a to b. The mass of the region is just the uniform density rho times the area of the region. And then the centroid, we denote x bar, y bar as the center of gravity, or the centroid, and the x coordinate is the moment of R about the y-axis divided by m, the mass, and the y coordinate of the centroid is the moment of R about the x-axis divided by m. Okay, so for this, let's see if we can find the location of the centroid of the region that is bounded by f of x equals x squared and y equals 0 on the interval from x equals 0 to x equals 1. Okay, the moment of that region about the y-axis is rho times the definite integral from 0 to 1 of x times f of x, so x times x squared dx. So we know that x times x squared is x to the third, so let's just go ahead and write down the antiderivative for x to the third, which is x to the fourth over 4. and then evaluate this from 0 to 1. When x is 0, the quantity is 0, so we'll just end up with 1/4 times rho. Okay, the moment of the region R, or the moment of this region about the x-axis, is denoted m sub x, and this is equal to rho times the definite integral from 0 to 1 of 1/2 times x to the second squared dx. So x to the second squared is just x to the 4th. So let's just go ahead and write down rho times 1/2, and then the antiderivative for x to the 4th, which is x to the 5th over 5. We evaluate this from 0 to 1. Once again, when x is 0, the quantity is 0, and then at x equals 1, we're just left with rho times 1/2 times 1/5, or 1/10 times rho. Then finally, the mass of the region. This is rho times the definite integral from 0 to 1 of the function f of x, which is x squared. So we get rho times x to the 3rd over 3 from 0 to 1. And this simplifies to 1/3 times rho. And now we can find the centroid, the center of gravity, x bar. That's equal to the moment about the y-axis divided by the mass. So 1/4 times rho divided by 1/3 times rho. And that simplifies to 3/4. And then the y-coordinate, that's the moment about the x-axis, 1/10 times rho divided by the mass, 1/3 times rho. And that simplifies to 3/10. So let's just sketch a graph of f of x equals x squared on that interval from 0 to 1. So f of x equals x squared will look something like this on the interval from 0 to 1. And the centroid the x-coordinate is 3/4, the y-coordinate is 3/10. If we did it correctly, x equals 3/4 is about right here. 3/10 is right in there. So at least we got a point that's in the region, so that's a pretty good sign. So that looks like that could be the center of gravity for that region. Okay, let's move on to the next page. So now we're on Chapter 9 material. So remember, separable differential equations. A separable equation is a first-order differential equation that can be written in the form dy dx equals g of x times f of y. So as a reminder, If it's separable, then you can separate the y parts from the x parts. Whoops. So dy over f of y, and that's equal to g of x dx. And then afterwards, we integrate the left-hand side with respect to y, integrate the right-hand side with respect to x. And then if there are any initial conditions, we apply those accordingly. Okay, so here's an example of a separable differential equation. Dy dx equals y plus 1 times the quantity 2x plus sine of x. And the conditions are that y is greater than -1. And the initial condition, y of 0 equals 2 plus e to the 5th. So what this means is when x is 0, the value of y is 2 plus e to the 5th. Okay, but first let's write it separated. So we'll divide both sides by y plus 1 and multiply both sides by dx. And we'll get dy over y plus 1 equals 2x plus sine of x, all multiplied by dx. I could put another step in where I put the integral symbols in, but let's just go ahead and find the antiderivatives. So just imagine an integral symbol, dy over y plus 1, so we get an antiderivative of the natural log of y plus 1. Since y has to be greater than -1, I don't need the absolute value symbols because y plus 1 will be positive if y has to be greater than -1. And then on the other side, find antiderivatives of 2x and sine of x. An antiderivative of 2x is x to the second. And an antiderivative of sine of x is negative cosine of x. And then put plus c for the constant of integration. The goal is to solve for y and then impose the initial condition. So at the moment, we have the natural log of y plus 1 equals x squared minus cosine of x plus c. So using a property of logarithms, we can write y plus 1 is equal to e raised to the exponent x squared minus cosine of x plus c. And so y is equal to e to the x squared minus cosine of x plus c, and then minus 1. Okay, we'll use the initial conditions to find the value of c. So when x is 0, the y value is 2 plus e to the 5th. So in the next step, what we'll do is we will replace y with 2 plus e to the 5th. And on the right-hand side, replace every x with 0. So we get e to the 0 minus cosine of 0. Well, cosine of 0 is 1, so we get, in the numerator, we get numerator. In the exponent, we get negative 1 plus c. And then don't forget the minus 1. So now add 1 to both sides to get 3 plus e to the 5th equals e to the, I'm going to rewrite e to the negative 1 plus c as e to the negative 1 times e to the c. And then divide both sides, or multiply both sides by e, because if we divide by e to the negative 1, that's the same as multiplying by e. So we get 3e plus e to the 6th equals e to the c. So this is kind of goofy, but if we rewrote this, we could put e to the c out front, and so we can just write this as y equals 3e plus e to the 6th times e to the x squared minus cosine of x, and then minus 1. Okay, the one on the final won't be as weird as this one is. Okay, let's move on to the first order linear differential equations. A first order linear differential equation can be written in the form dy dx plus p of x times y equals q of x. And when it's in this form, we find the integrating factor, which we use capital I of x to refer to. The integrating factor is e to the integral of p of x dx. Once we find the integrating factor, we multiply both sides of this equation, and that will enable us to find an antiderivative to help solve the differential equation. Okay, so we're given a first order linear differential equation that's in the form that we want. So in this one, p of x is 1 over x. And so the integrating factor is e to the integral of 1 over x dx. But an antiderivative of 1 over x is the natural log of x. And e to the natural log of x is just x. Then we multiply both sides of the original equation by x. So we get x times dy dx. And then x times 1 over xy simplifies to y. And on the right-hand side, x times 1 over x squared is 1 over x. And the left-hand side is the derivative of a product. So if we rewrite x times dy dx plus y as the derivative with respect to x of the product x times y, and that's equal to the right-hand side 1 over x. And since the left-hand side is the derivative of the product xy, we integrate both sides. And when we integrate the left-hand side with respect to x, we get x times y. And then we integrate the right-hand side with respect to x. And this here we get the natural log of x. plus a constant. The goal is to solve for y. So we get y equals the quantity, the natural log of x plus the constant of integration all divided by x. And we have an initial condition, y of 1 equals 5. That means that when x is 1, y is 5. So in this equation, replace y with 5 and x with 1. So we get 5 equals the natural log of 1 plus c divided by 1. The natural log of 1 is 0, so 0 plus c divided by 1 is c. So c is just the number 5. And so the function that we want with c equals 5, we write that as y equals the natural log of x plus 5 all divided by x. Okay, let's get started on the chapter 10 material. Okay, so the following 4 examples all use the parametric curve defined by x equals t plus 2, y equals t to the second minus 2t for values of t that are between -1 and 3. In the first part, eliminate the parameter to find a Cartesian equation of the curve. The parameter is t, so we want an equation for the curve that's in terms of x and y only. So the easiest thing to do is first solve x equals t plus 2 for t. So t is equal to x minus 2. And then in the other equation, instead of y equals t squared minus 2t, we have y equals, replace t with x minus 2. So we have y equals x minus 2's quantity squared minus 2 times the quantity x minus 2. So this is an okay equation, but we can expand it a little bit. X minus 2 quantity squared is x squared minus 4x plus 4. And then we subtract 2x and subtract -4 or add 4. And then we can write it in simplified form, y equals x squared minus 6x plus 8. Then it says find an equation of the tangent line corresponding to t equals 2. So here we remember in order to find the slope of a tangent line, we need to know the derivative. So if y and x are defined by parametric equations, the derivative of y with respect to x is equal to the derivative of y with respect to t divided by the derivative of x with respect to t. So y is t to the second minus 2t, so the derivative of y with respect to t is 2t minus 2. And in the denominator, since x equals t plus 2, the derivative of x with respect to t is just 1. And we want to know the slope of the line when t is 2. So just replace t with 2 and do the arithmetic. 2 times 2 is 4. 4 minus 2 is 2. 2 over 1 is 2. So that's the slope of the line. And then we need to know the x and y coordinates that correspond with t equals 2. When t equals 2, the x coordinate is 2 plus 2, or 4. And the y coordinate, when t equals 2, is 2 to the second minus 2 times 2. 4 minus 4 is 0. So if we use the point slope form, y minus y1 equals m times x minus x1, with the ordered pair xy equals 4, 0, or I should say x1, y1, then we get y minus 0 equals 2 times the quantity x minus 4. Okay, we're out of time. We'll pick up right here tomorrow. So go ahead and sign in for attendance.